What's good guys, I welcome you to my YouTube channel Jack Physicist. In today's video, we will learn length contraction, time dilation and invariant of spacetime. Let us draw a graph to understand length contraction. In this graph, there are two reference frames. One is stationary, which is described by normal x and t axis, while the bent one is moving reference frame, described by x prime and t prime. We draw a stick from origin to 2c represented by two dots. Its length is 2c at time t is equal to 0. Now we draw the same stick but at t prime is equal to 0. At t prime is equal to 0, stick will look something like this. Now graphically it seems stick at t prime is equal to 0 is longer than stick at t is equal to 0, but it is the same stick. Difference is that ends of stick at time t is equal to 0 were at same time and ends of stick at time t prime is equal to 0 are at different time. This means if these are same sticks, then their length must be equal, right? Not actually. Let's see how. According to Lorentz transformation, x prime is equal to x minus vt upon under root 1 minus v square. For stick at t prime is equal to 0, t is equal to vx. X prime is equal to x into 1 minus v square upon under root 1 minus v square, which on simplifying gives us x prime is equal to x into under root 1 minus v square. Here x prime is the length of the stick in moving reference frame, while x is length of stick on stationary reference frame. Now don't forget, v square is always less than 1 as any object can travel faster than speed of light, which is 1 in this case due to the units. Subtracting anything less than 1 from 1 and then doing its square root always gives a number less than 1. You can take an example to understand it clearly. Let us take velocity of other reference frame b 0.8. So x prime is equal to x into under root 1 minus 0.64 and x prime is equal to x into under root 0.36. Finally, x prime is equal to x into 0.6, which means whatever x is, x prime will always be less than x. Hence, in above given case, stick at t prime is equal to 0 is shorter than the stick at t is equal to 0. Now let's talk about time dilation. Time dilation is somewhat similar to length contraction. We assume two observers, one is stationary while other is moving. Let us describe 3 seconds passing for both the observers graphically. On time axis, 3 seconds are these big. Now according to Lorentz transformations, t prime is equal to t minus vx upon under root 1 minus v square. Now in our case, x is 0, so t prime is equal to t upon under root 1 minus v square, where under root 1 minus v square is always less than 1. Dividing anything less than 1 will always give larger number than the original. So t prime is greater for any observer moving with a velocity v. Now for a person moving with velocity 0.5 where c is 1, let t be 3 seconds. Substituting these values in the equation, we get that t prime is ultimately longer than t. So this point in the graph describes 3.48 seconds. That is part for time dilation. If you're struggling with some of the concepts we've covered or need more personalized help, I'm here to support you. Reach out to me for one-on-one coaching sessions. You can contact me through Instagram, Gmail or leave a comment right here on YouTube. Let's tackle those challenges together. So far we have seen distance and time is not invariant in different reference frames. One thing common to reference frame is origin, so let us see if distance from origin is the same. If distance from origin of any point for both reference frame is same, then x square plus t square must be equal to x prime square plus t prime square. Let us substitute values of x prime and t prime from Lorentz transformations. We get that x square plus t square is clearly not equal to x prime square plus t prime square. But if you observe equations clearly, you can see that the extra term can be cancelled if there was a negative sign between t prime square and x prime square. Let's substitute Lorentz transformations into t prime square minus x prime square is equal to t square minus x square. We get that in fact t prime square minus x prime square is equal to t square minus x square. Hence distance from origin is invariant of reference frame, which is given by the relation t prime square minus x prime square is equal to t square minus x square, and not the Euclidean distance between origin. line. This is known as spacetime interval, denoted by tau. In XT graph, this simply means the line connecting any point to origin, but in real life it has another meaning. Let us see that by relating it to movie Interstellar. I am assuming you all have seen that movie. Even if you haven't, you will understand this. So in that movie, a team goes to a planet near to black hole, hence their time slows down. If that team stays on the planet for 1 hour, 7 years passes on Earth. Here, if 7 years is amount of time passed at Earth, it is time coordinate t, while proper time is 1 hour for the team at the planet. This means proper time is a clock that is attached to the observer and it ticks at the same time at every place. You can say it is the time responsible for evolution or aging. From my eye, I will only live around 100 years, doesn't matter if that's on Earth or in any other place. I hope you now understand the meaning of proper time, at least a little. In the Interstellar movie, the difference in the time experience is due to time dilation, but not the equation we derived, as that was for special theory of relativity. To calculate time dilation in the movie, equation from general relativity is used. That is it for today, guys. In the next video, we will discuss two reference frame problem to kind of prove constancy of speed of light using Lorentz transformations. And we will also discuss light cones, space-like interval and time-like interval. Until then.